Hello everyone. In this video we're going to go over section 4.3 class node problems. So first, we want to determine if a list of numbers is going to be rational or irrational. And if it is, expressed as the a over b form where a and b are integers with b different from 0. Notice that pretty much that's the definition from the first number, 7 over 3. Clearly 7 and but 3 are integers. And 3 is different from 0. So it is, by definition, rational. So 7 over 3 belongs to the rational numbers. Minus 12 is also a rational number. You can see this as minus 12 over 1. And in that way, you have two numbers both that belongs to the natural numbers. To the rational number, to the integers, and the denominator is different from 0, so that's going to belong to the rationals. Now 0.25 can be seen as 25 over 100. Notice that once again these are two integers with the denominator different from 0, and hence 25 over 100, which is 0.25, belongs to the rational numbers. Now 0.6 repeating is also a rational numbers. Remember that if we have a repeating pattern, then we can express this as a rational number. One way of doing this is if I see x equals 0.6 repeating, then I can multiply this by x. So 10x is just going to be 6.66 or 6.6 periodic. And so if I do a subtraction here between 10x and 9x, I'm just going to have that this is 6. And so pretty much I got 9x is 6, and I can see x being 6 over 9. So this is going to be simplifying 2/3. Notice that these are two integers, and the denominator is different from 0, so it's going to belong to the rational numbers. Now square root of 9 is 3, and 3 can be seen as 3 over 1. And so both 3 and 1 are integers. 1 is different from 0, so that means that the square root of 9 is going to belong to the rational numbers. Now, square root of 7 is an irrational. It cannot be expressed in the form p over q. Now, let's go and write certain decimals as a quotient of integers. So notice all of these numbers are either are decimals that are finite, so they're going to be rational numbers. I can write 0.75 as 75 over 100. And this is one way of writing as a quotient of integers. Of course, I can simplify this. And this will be 3 over 4. And so this is a simplified version. Now 2.5, I can also write it as 25 over 10, which simplify is 5 over 2. One way that always we can transform this is we multiply the top and the bottom by something. So for example, 2.5 multiplied by 10 is 25. And so we can multiply up and down by 10, and that's giving me this. This one I'm multiplying up and down by 100. Now I'm going to do this with 1,000. So I'm just going to multiply up and down by 1,000. So this is going to be 125 by 1,000. I can simplify this, and this is going to be 1 over 8. This minus 3.4, I can do exactly the same. I can multiply this by 10, and it's going to be minus 34. And because I multiply by 10 up, I'm going to multiply by 10 down. And I have this. I can simplify this to minus 17 over 5. So these are good ways of putting decimal numbers into rational form. Now we have repeating patterns like in question number 3. We gotta look for how many decimals do we have. So if x is 0.27 and we have the repeating pattern of 27, I can multiply by the number of decimals that I have here. So because I have 2 decimals after the 0, then I can multiply by 100. And if I multiply by 100, that's going to give me 27.27. And so the pattern is going to keep repeating, but I'm going to have an integer here, an integer number here. And so now I can do 100x minus x. And this is going to be, of course, on one side, it's going to be this minus this. So it's going to give me 27. It's just going to give me the integer part. And here I'm going to get 99x. So pretty much what I'm saying now is that 0.27 periodic can be expressed as 27 over 99. I can simplify this, and this will be 3 over 11. Okay, now let's go to question number 4. Question number 4 is just a reminder of the stuff we done in class. So we want to write, using quantifiers and variables, the 0 product property, which is pretty much that for all x and y that belongs to the real numbers, if x different from 0 and y is different from 0, then x times y is different from 0. Now the contrapositive for this will be that for all x, y that belongs to the real number, if then the contrapositive will be the negation of this. If x times y is equal 0, then it's because x is equal 0 or y is equal 0. One of them is going to be 0. This x different from 0, comma, y equals different from 0 is like an and. So when I'm negating here, this is going to be transformed into an or. The informal English version of the contrapositive, it will be if the product of two numbers, of two real numbers, is 0, then one of them is 0. Then now, question number 5. Prove every integer is a rational number. Well, if we have an integer, remember, we have an integer given n that belongs to the integers. And this is, once again, a direct proof. So we go with the assumptions. Given an n that belongs to the integers, then n can be seen as n over 1. And this is at the same time both the definition of the assumption and at the same time is a manipulation. And now notice that I'm seeing this as n over 1, which is the definition of the conclusion, because we're seeing this as a fraction of two integers. One is different from 0. And so we're seeing n as a fraction where both numbers are integers. The denominator is different from 0. So this is by conclusion n over 1 equals n belongs to the rational numbers. Okay. Now for question 6, we have prove the difference of any two rational numbers is a rational number. And says uses the fact that subtraction is addition of the negative. So first, let's go with the assumptions. Let's pick two rational numbers, R and S, that belongs to Q. Then step number 2, definition of the assumptions. Then R gotta be P over Q, and S gotta be A over B, with P, Q, A, B that belongs to the integers, and QB gonna be different from 0. So now the manipulation step will be R minus S, which will be P over Q minus A over B. And if we get a common denominator, we multiply everything here for b and everything here for q, we get p over b, q over b, minus a times q, a times q, b times q. And so now with common denominator, this is going to be bb minus aq over bq. Notice that because q and b are different from 0, bq are going to be different from 0 because the set of product property. And because these are integers here and integers here, then this is going to be the definition of the conclusion that r minus s is just going to be a fraction of k over m that is going to belong to the rationals, where we have that both this is an integer and an integer, and this integer is different from 0. So as a conclusion, r minus s belongs to the rational numbers. Now, last for this video, if we have that r is a non-zero rational number, then 1 over r is rational. So if r is different from 0 that belongs to the rationals, notice that this is going to be our assumption. So by definition of the assumption, step number 2, r is going to be a p over q. And notice that by my hypothesis of being a rational, I know that q is different from 0, but also because the rational is different from 0, since r is different from 0, implies p is different from 0. So both p and q are going to be different from 0. So now my manipulation is going to be find out what is 1 over r. But 1 over r is just going to be q over p. And notice that both q and p are integers, and p is going to be different from 0. So that means that q over p belongs to the rationals. And so that implies, and this is my definition of the conclusion, and my conclusion will be that 1 over r belongs to the rational numbers. So I have all the steps of the proof for this. Okay, let's continue the examples on video number 2.